2 years ago, our star began behaving in a way that caught nearly every solar physicist off guard. Auroras that should only ever be visible near the poles lit up skies as far south as Florida and the Bahamas. Satellites drifted off course, and power grid operators watched their monitoring systems flicker with unexpected currents. The culprit was the sun entering the explosive peak of its current cycle, a phase known as solar maximum, and it arrived nearly twice as intense as forecasters had predicted only a few years earlier. Since then, researchers have been racing to figure out why our models were so wrong, and what they have found has forced a rethink of some very basic assumptions about how the sun works, where its magnetic engine actually sits, how well we can even measure that engine, and what is really happening at the solar poles that we have almost never been able to see. To understand why this matters, it helps to first understand what a solar cycle actually is. Roughly every 11 years, the sun swings between two very different states. During solar minimum, the surface is relatively calm, with few sunspots and comparatively little eruptive activity. During solar maximum, the surface becomes chaotic, peppered with dark, magnetically intense sunspots, and prone to violent outbursts called solar flares and coronal mass ejections, both of which are often grouped together under the umbrella term solar storms. Sunspots have been used as a rough proxy for the sun's magnetic activity for centuries, ever since astronomers like Heinrich Schwab and later Rudolf Wolf began systematically counting them in the 1800s. More sunspots generally means more magnetic tangling, which in turn means more flares and more ejections of solar material into space. The current cycle, numbered cycle 25 by the convention astronomers have used since they began formally tracking these periods, began around the year 2020. From the outset, it started to look unusual. By August of 2024, observers counted 216 sunspots in a single month, nearly double what the original forecast had called for, and the highest monthly count seen in 23 years. That kind of overshoot demanded an explanation, because the method scientists use to forecast solar cycles is not a guess, it is grounded in real physics. And until recently, it had a fairly solid track record. The forecasting method in question relies on something called the polar field precursor technique. Here is the basic idea. As sunspots emerge and eventually decay over the course of a cycle, the magnetic flux they carry does not simply vanish. Instead, it slowly migrates toward the sun's north and south poles, where it accumulates into a coherent, large-scale magnetic field. The strength of that polar field, measured right around the point of solar minimum, turns out to be a remarkably good predictor of how strong the next cycle will be. Weak polar fields, at minimum, tend to produce weak, quiet cycles. Strong polar fields tend to produce violent, sunspot-heavy cycles. To measure this polar field, scientists have long relied on an instrument called the helioseismic and magnetic imager, usually just called by its acronym, flying aboard a spacecraft called the Solar Dynamics Observatory, which has been staring at the sun from Earth orbit since 2010, sending back a continuous stream of some of the most detailed solar images ever captured. Using that instrument's data, a panel of experts convened jointly by NASA and the National Oceanic and Atmospheric Administration sat down in 2019 and reviewed a range of independent forecasts for the coming cycle. Their consensus was that cycle 25 would peak at around 115 sunspots. A fairly weak and unremarkable maximum, this was not an unreasonable call at the time. The three cycles before it, numbered 22, 23, and 24, had each been progressively weaker, with cycle 24 turning out to be the feeblest solar maximum in roughly a century. A continuation of that downward trend seemed like the safe bet. Then came a discovery in 2025 that upended the picture entirely. A team at the National Solar Observatory built a detailed virtual simulation of the helioseismic and magnetic imager itself, feeding it synthetic magnetic field data with known, controlled properties, essentially testing the instrument against ground truth it had helped create. The result was unsettling. The simulated instrument was only picking up roughly half of the actual magnetic field strength present at the poles. If the real instrument in space has been suffering from the same blind spot for well over a decade, then every polar field measurement used to forecast solar cycles since 2010 has likely been an underestimate, which would neatly explain why cycle 25 ended up so much stronger than expected. But an instrument calibration problem, even a significant one, does not fully account for the size of the discrepancy. Something more fundamental appears to be going on with how the sun generates its magnetic field in the first place. Ever since Galileo first turned a telescope towards sunspots in the early 1600s, astronomers have wondered what actually powers the sun's magnetism. For most of the 20th century, the leading explanation placed the source deep inside the star, at a boundary layer called the tachocline, sitting roughly 200,000 kilometers beneath the visible surface. This is the transition zone between the sun's radiative interior, where energy moves outward through radiation alone, and its convective outer layers, where hot plasma physically churns and rises like water boiling in a pot. At the tachocline, different layers of the sun rotate at different speeds, a phenomenon called differential rotation. The classic theory held that this differential rotation stretches and winds up magnetic field lines, the way twisting a rubber band stores energy, and that this winding process generates the dynamo, responsible for everything we see happening on the surface above in 2024. A collaboration of researchers from institutions including the Massachusetts Institute of Technology, Northwestern University, and the University of Edinburgh challenged this long-standing picture. Using one of NASA's most powerful supercomputers, they ran the most detailed simulations of solar plasma dynamics ever attempted, modeling the physics of the sun's interior with a level of resolution that simply was not computationally possible in earlier decades. Their results pointed to a very different origin point for the dynamo. Not 200,000 kilometers down at the tachocline, but a comparatively shallow 32,000 kilometers beneath the surface. This distinction matters enormously, because a dynamo operating that close to the surface would be driven by a completely different physical process, something called magneto-rotational instability. This phenomenon occurs when a relatively weak magnetic field links to layers of plasma that are rotating at different speeds. Rather than damping out that difference in rotation the way you might intuitively expect a magnetic tether to behave, the field actually amplifies the difference, driving increasingly turbulent motion that in turn sustains and strengthens the magnetic dynamo. It is a self-reinforcing feedback loop, and one with a critical advantage over the older tachocline model. It produces specific, testable predictions. The tachocline model, for all its intuitive appeal, relied on assumptions about deep interior conditions that were poorly constrained by observation. Since we cannot directly see 200,000 kilometers into the sun, a near-surface dynamo driven by magneto-rotational instability, by contrast, would help explain why consecutive solar cycles can vary so dramatically in strength and character, something the older model struggled to account for cleanly. It offers a mechanism grounded in plasma physics that can be checked against real data, gathered much closer to where the action is actually happening, which brings us to one of the most remarkable spacecraft ever built, a probe that flew close enough to the sun to test these ideas directly. In 2018, NASA launched the Parker Solar Probe, named in honor of the astrophysicist Eugene Parker, whose ideas we will return to shortly. Among its central science goals was studying the sun's magnetic dynamo and the physics of the solar wind up close, rather than inferring their properties from measurements taken millions of kilometers away near Earth. After a journey of nearly 3 years, using repeated gravity assists from Venus to gradually tighten its orbit, the probe arrived in its working orbit in April of 2021, just as the sun was beginning its ramp up toward the current maximum. What it has observed since then, from deep inside the sun's outer atmosphere, has reshaped our understanding of how the active sun actually behaves. On Christmas Eve of 2024, the Parker Solar Probe made its closest approach yet to the sun, skimming through the outer corona and the streaming solar wind at a distance of only about 6 million kilometers above the surface, an almost unimaginably close pass for any human-made object at its peak speed during that flyby. The probe was moving at close to 700,000 kilometers per hour, making it the fastest object humans have ever built. Impressive as that speed record is, it is not actually the most scientifically important part of the mission. Over the course of 27 separate orbits, the probe has slowly assembled a body of data that appears to solve a puzzle that has frustrated solar physicists for the better part of a century. The mystery of why the sun's outer atmosphere is so much hotter than its surface. The visible surface of the sun sits at a temperature of about 5,500 degrees Celsius, yet the corona, the tenuous outer atmosphere that extends far beyond that surface, reaches temperatures ranging from about 1 million degrees Celsius up to a staggering 10 million degrees in certain active regions. Simple thermodynamics says heat should flow from hot to cold. So an atmosphere far hotter than the surface it surrounds seems to break the rules, unless some additional energy source is heating the corona directly. Researchers long suspected magnetism was somehow responsible, but exactly how remained frustratingly unclear. Part of the picture involves structures called large convective cells on the sun's surface where hot plasma rises, spreads, and sinks back down. Similar in concept to the boiling pattern on the surface of a pot of water, just vastly larger and driven by nuclear fusion rather than a magnetic field lines tend to concentrate and strengthen at the boundaries between these When that concentrated field becomes strong enough, it can interact violently with the surrounding plasma, launching narrow jets of material and tiny, rapid bursts of energy called nanophotons. In places where the field is especially intense, it can rupture straight through the surface, producing the dark sunspots we can observe from Earth, and forming enormous looping magnetic structures that arc up into the atmosphere. Most of these magnetic loops are closed, meaning both of their ends remain anchored to the sun's surface. But in certain regions, the loops are torn open instead, stretching outward without a matching anchor point, extending all the way to the edge of the heliosphere, the vast bubble of solar influence that encompasses our entire solar system. These are called open magnetic field regions, and they turn out to be central to the corona heating puzzle. Back in 1988, the astrophysicist Eugene Parker, working at the University of Chicago, proposed an idea that seemed radical at the time. He suggested that the churning convective motion of supergranules on the sun's surface does not just open and close these magnetic field lines passively. It actively tangles them over time. This tangling builds up stored magnetic energy in the solar atmosphere until the twisted field lines eventually buckle, snap apart, and reconnect in a new configuration. A process called magnetic reconnection. Each reconnection event releases its stored magnetic energy explosively, converting it directly into heat within the surrounding plasma for decades. This idea was largely dismissed by Parker's peers as speculative. It took a spacecraft bearing his own name, flying directly through the environment he theorized about, to finally provide the vindication his idea had been waiting for. Even so, well into the 21st century, puzzling anomalies kept appearing in our data about the Sun's magnetism. The European Space Agency's SOHO mission, launched in the mid-1990s, revealed that the Sun's magnetic field was considerably more variable and complex than researchers had assumed, and measurements of solar wind particles taken near Earth showed strange compositional signatures that did not line up neatly with the prevailing theory, which held that solar wind material originated primarily from the Sun's visible surface. It has taken the Parker Solar Probe, flying directly through this environment rather than observing it from a distance, to finally connect these seemingly disconnected observations into a coherent story. Its onboard imaging instrument, called the Wide Field Imager for Solar Probe, or WISPR for short, revealed something unexpected about the structure of the solar wind. From near Earth, the solar wind looks like a fairly uniform, turbulent stream of charged particles, but viewed up close, from within the corona itself, it actually flows outward in distinct individual streamlets, and the size of these streamlets closely mirrors the size of the supergranules on the surface far below. With every successive orbit, the probe examined these outflowing streams in finer detail, and found something rather strange embedded within them. The streamlets carry clear signatures of magnetic activity, but the magnetic field lines within them are twisted into an odd, sharply folded S-shaped pattern. Scientists have named these structures switch, and they appear to form when closed magnetic loops collide and merge with open magnetic loops in an event known as interchange reconnection. These reconnection events release heat and eject material outward into space, both warming the corona from within and accelerating the particles that make up the solar wind. A mechanism that lines up remarkably well with what Eugene Parker had proposed roughly 4 decades earlier, long before anyone could confirm it directly. Until quite recently, the standard model of coronal mass ejections assumed that ejected solar material only ever traveled in one direction, outward from the Sun into space. But during that same December 2024 flyby, the Parker probe captured footage of something that did not fit that simple picture at all. A cloud of ejected solar material burst outward from the star, only to curl back inward and fall in what looks like a U-turn, returning toward the Sun rather than escaping into space. According to analysis released by NASA, material that falls back onto the Sun in this way can subtly alter the surrounding solar atmosphere, and those alterations can go on to influence how future coronal mass ejections erupt and evolve. Hints of this kind of inflow had been glimpsed before, in older data from the SOHO and STEREO missions, but never captured with anything like this level of resolution or clarity. Armed with this new data, researchers will be able to precisely characterize the speed, shape, and size of these inflow events, refining our ability to forecast solar cycles and space weather with much greater confidence than before. The Parker Solar Probe has effectively shown us the Sun from the inside, revealing how magnetic energy accumulates, erupts, and resets over the course of each 11-year cycle. But its orbit keeps it aligned close to the Sun's equatorial plane, meaning it cannot give us a direct view of the magnetic hubs at the poles, which turn out to be just as important to the story. To get that view, a different spacecraft had to venture somewhere almost nothing has gone before. Most spacecraft, including most planetary orbiters and solar observatories, travel within what is called the ecliptic plane, the flat disk traced out by the orbits of the planets around the Sun. Because of this, for the entire history of space exploration up until quite recently, humanity had only ever observed the Sun's poles from the side, at a steep, distorted angle, somewhat like trying to read the numbers on a clock face while standing off to one side rather than looking at it head-on. The European Space Agency's Solar Orbiter mission was designed specifically to correct that blind spot, using a carefully choreographed series of gravity assist maneuvers past Venus. Solar Orbiter has gradually tilted its orbit further and further out of the ecliptic plane with each successive pass, climbing 2 steadily higher solar latitudes. On the 23rd of March, 2025, it finally crossed 17 degrees below the solar equator, locked its instruments onto the sun's south pole, and captured the very first images ever taken of that region. What those images revealed was a chaotic, tangled environment, and they contained 3 major surprises that scientists are still working through. The first surprise concerns basic magnetic structure. An ordinary bar magnet has a clearly defined North Pole and South Pole, with field lines that point in a single, consistent direction at each end. Solar Orbiter revealed that, for a period during solar maximum, the Sun's south pole actually hosts both north polarity and south polarity magnetic fields simultaneously, tangled together in the same region rather than cleanly separated out of this bubbling magnetic chaos. The Sun eventually reorganizes its entire global magnetic field, flipping polarity so that what was the north magnetic pole becomes the south, and vice versa. This flip happens roughly once every 11 years, meaning it actually takes 22 years to full sunspot cycles for the Sun's magnetic field to return to its original orientation. This longer 22-year cycle is known as the Hale cycle, named after the astronomer George Ellery Hale, who first identified the polarity reversal pattern in sunspots in the early 20th century. Once the flip completes, a single dominant polarity gradually builds up and settles at each pole, reaching its most stable, orderly configuration right around solar minimum, precisely the period when the Sun's overall activity is at its quietest. The second surprise came from an instrument aboard Solar Orbiter called the Spectral Imaging of the Coronal Environment Instrument, generally referred to by its acronym. This spectrometer mapped how quickly clumps of solar material were moving through the transition region of the polar atmosphere, a thin, irregular layer where temperature rapidly jumps from around 10,000 degrees Celsius to hundreds of thousands of degrees over a very short distance. The instrument works by detecting the specific wavelengths of light emitted by different elements, including oxygen, neon, carbon, and hydrogen, each of which glows at particular temperatures. By tracking how these signatures shift and move, scientists were able to build the first ever direct velocity map of material near the Sun's south pole. This matters because it represents the first time researchers have traced the solar wind directly back to its actual point of origin, rather than reconstructing its properties after the fact from measurements taken millions of kilometers downstream, closer to Earth. The third surprise ties directly back to why solar cycle 25 turned out so much stronger than forecasters expected. A paper published in November of 2025, based on Solar Orbiter observations, found evidence that the poleward migration of sunspot magnetic fields, the same process underlying the polar field precursor forecasting method described earlier, may be happening considerably faster than existing models assumed. This has major implications for how we forecast future cycles, because the speed and strength of that poleward drift during one cycle directly determines the polar field strength present at the following solar minimum, which in turn determines how strong the next cycle will be. If magnetic flux is reaching the poles faster than our models predict, then our estimates for the strength of upcoming cycles could be off before the forecasting process even properly begins. Taken together, these threads suggest that solar cycle 25 was underestimated for several compounding reasons at once. The instrument used to measure polar magnetic fields appears to have been detecting only a fraction of the true signal for well over a decade. The underlying theory of where and how the sun's dynamo actually operates may have been fundamentally incomplete, and the rate at which magnetic flux migrates toward the poles may be considerably faster than existing models assumed. Any one of these factors alone might explain a modest forecasting error. All three together go a long way toward explaining why cycle 25 came in nearly double the strength originally predicted. Fortunately, none of the largest flares or ejections from this unexpectedly strong cycle have struck Earth head-on with full force. But the storms that did arrive were still powerful enough to reveal in vivid detail just how vulnerable our technology-filled world is to space weather, and just how much damage a truly severe event could cause. On the 10th of May, 2024, a major geomagnetic storm struck Earth. Storms like this begin when the sun releases a coronal mass ejection, hurling roughly 1 billion tons of magnetized plasma outward into space. It typically takes several days for that material to cross the distance to Earth, but once it arrives, it slams into our planet's magnetosphere, the protective magnetic bubble surrounding Earth, triggering a rapid and often violent transfer of energy between the incoming solar wind and the space environment immediately around us. The visible result was spectacular. Auroras, normally confined to high-latitude regions near the poles, blazed as far south as the Florida Keys, the Yucatan Peninsula in Mexico, the Bahamas, Jamaica, Puerto Rico, and Hawaii, sightings that would have seemed almost unbelievable just a decade earlier. A month later, a fainter reddish aurora appeared over Japan, and subsequent analysis found it had extended far higher into Earth's atmosphere than expected, reaching altitudes of around 800 kilometers, a sign that the charged particles involved carried considerably more energy than scientists had initially assumed. Beautiful as these light shows are, geomagnetic storms pose real risks precisely because of how they disturb Earth's magnetosphere. Surrounding our planet is a region called the plasmasphere, a bubble of relatively cool, dense charged particles that help shield us from incoming solar material. When a geomagnetic storm strikes, the pressure of the solar wind compresses this plasmasphere inward, squeezing it the way a deflating balloon shrinks under external pressure. After the storm passes, the plasmasphere is normally replenished from below, refilled by charged particles rising up from the ionosphere, the layer of Earth's upper atmosphere where solar radiation strips electrons from atoms, creating a soup of ions and free electrons. The May 2024 storm turned out to be the strongest in 21 years. And by sheer good fortune, a Japanese satellite called auroras happened to be perfectly positioned to observe its effects on the magnetosphere in unprecedented detail. A research team led by Dr. Otsuki Shinbori at Nagoya University's Institute for Space, Earth Environmental Research obtained the first continuous, direct measurements ever recorded of the plasmasphere, collapsing down to a dramatically low altitude during a storm of this magnitude. Data showed the outer boundary of the plasmasphere collapsing from about 44,000 kilometers down to just 9,600 kilometers in under 9 hours, shrinking to roughly 1/5 of its normal size. This was the lowest altitude ever recorded for the plasmasphere's outer boundary since the ARACE mission began operating in 2017. That collapse left virtually every satellite in geostationary orbit, along with most spacecraft in medium Earth orbit, severely exposed to the full brunt of the storm, a category that includes many weather monitoring satellites, television broadcasting satellites, communications relays, and the constellations that make up our global navigation satellite systems. At the storm's peak, interference directly affected GPS frequency bands, producing position errors, data gaps, and tracking failures across large stretches of global airspace, with hundreds of aircraft over Europe alone experiencing measurable disruption. Disturbances in the ionosphere grew severe enough that sudden, unexplained jumps appeared in recorded aircraft flight tracks. Openly published tracking data from the United States Space Force later revealed that more than 5,000 satellites had to perform maneuvers to adjust their positions during the storm, in order to avoid the risk of deorbiting uncontrolled or colliding with other objects. This kind of risk compounds on itself, because a single satellite collision can generate thousands of fragments of space debris that can persist in orbit for decades, each fragment representing a further collision risk to everything else sharing that orbital region. Perhaps the most striking finding from this event, though, was what happened in the storm's aftermath. Under normal circumstances, a compressed plasmasphere takes only 1 to 2 days to refill and return to its typical size. This particular storm hit the plasmasphere so hard that full recovery took more than 4 days, roughly twice as long as expected, and researchers wanted to understand why. The explanation turned out to involve a chain reaction in the upper atmosphere. Roughly an hour after the solar wind first struck, intense heating near Earth's poles drove a surge of charged particles toward the polar caps. This sudden pulse of heating churned the upper atmosphere much like a powerful convective engine, dredging up heavier molecular gases, particularly nitrogen and molecular oxygen, from lower altitudes up into regions where they do not normally exist in significant quantities. Under ordinary conditions, the upper ionosphere is dominated by atomic oxygen ions, a relatively light and simple species. But when nitrogen and molecular oxygen flood into that same region, they react chemically with the atomic oxygen ions already present, reducing their overall concentration. Scientists call this kind of disruption a negative ionospheric storm, and in this case, it created a serious downstream problem. Atomic oxygen ions play a critical role in refilling the plasmasphere. After a geomagnetic storm, the process works like this. When a positively charged oxygen ion collides with a neutral hydrogen atom in the ionosphere, it strips away the hydrogen atom's electron. Since oxygen has a stronger pull on electrons than hydrogen does, this ionizes the hydrogen atom, turning it into a hydrogen ion that then rises upward along Earth's magnetic field lines into the plasmasphere, replenishing it. But with the population of oxygen ions depleted by the negative ionospheric storm, this entire production chain was effectively choked off at its source, slowing the normal upward flow of plasma into the plasmasphere to a trickle, and stretching the recovery time out far beyond what researchers had previously observed. This was the first time scientists had directly and conclusively established a link between negative ionospheric storms and this kind of delayed plasmasphere recovery, a finding with real implications for how long our technology remains vulnerable after a major storm passes. The sun was not finished either. Just a few days after the May 10th storm, an enormous X-class solar flare erupted, X-class being the most powerful category on the standard solar flare classification scale. Despite the disruption it caused to technology here on Earth, this particular flare only ranked at about an 8.7 on that scale. For context, the strongest flare ever recorded, which occurred back in 2003, was estimated at a magnitude of around 45, nearly 5 times stronger than the May 2024 event. And yet, even that record-setting 2003 flare pales in comparison to the most powerful geomagnetic storm in recorded history, the Carrington event of 1859. We do not have a formal flare magnitude for that event, since instruments capable of measuring flares in that way simply did not exist yet. But historical accounts describe the resulting geomagnetic storm striking Earth with enough force that telegraph operators around the world reported sparks jumping from their equipment. And in some documented cases, telegraph wires burst into flame entirely, all from induced electrical currents flowing through the wires themselves. Modern researchers have modeled what a Carrington-scale event would do if it struck a heavily electrified, technologically dependent society like ours today, rather than the sparse telegraph networks of the 1850s. Estimates suggest total damages in the United States alone could range from $600 billion up to $2.6 trillion, with somewhere between 20 million and 40 million Americans losing power. How long that outage would last is much harder to pin down, with estimates ranging anywhere from 16 days to as long as 2 years, depending heavily on how quickly damaged transformers and other critical grid infrastructure could be repaired or replaced. What makes an event like this especially frightening is how little warning time we would actually have. The single most important factor determining how damaging an incoming coronal mass ejection will be is the orientation of its embedded magnetic field. If that field points southward, opposite to Earth's own magnetic field near the equator, it connects far more efficiently with our planet's magnetosphere, dramatically increasing the chances of a severe geomagnetic disturbance. The trouble is, we cannot actually measure that orientation until the incoming solar material reaches a location called the L1 Lagrange point, a gravitationally stable spot roughly 1.5 million kilometers from Earth, positioned directly between Earth and the Sun, where a spacecraft can effectively hover in place relative to both bodies without needing constant course correction. By the time solar material reaches that measurement point, we would typically have only somewhere between 15 and 60 minutes to prepare and respond. An extraordinarily narrow window for something with potentially trillion-dollar consequences. While Earth's thick atmosphere and strong magnetic field offer meaningful protection for people on the surface, even during a severe storm, the situation is very different for astronauts working beyond that protective shield. If a major solar event occurs while a crew is in space, radiation levels inside their spacecraft can spike significantly. Cumulative exposure over a career in space raises long-term risks, including cancer and other health complications that can affect cognitive function and overall performance. This concern was a significant factor in the planning of NASA's recent Artemis II mission, during which each astronaut was equipped with a personal radiation dosimeter inside the Orion crew capsule itself, a system called the Hybrid Electronic Radiation Assessor contained 6 separate radiation sensors positioned throughout the cabin, continuously measuring dose rates in different locations. If radiation levels rose beyond safe thresholds, Orion's onboard systems would display visual warnings accompanied by an audible alarm, giving the crew immediate awareness of a developing radiation hazard. Given stakes this high, a considerable amount of effort is now going into building better early warning systems for space weather. On the 23rd of January, 2026, a dedicated space weather satellite operated by the National Oceanic and Atmospheric Administration arrived at the L1 Lagrange point. This spacecraft carries advanced instrumentation designed to continuously measure solar wind properties, thermal plasma characteristics, and magnetic field orientation in real time. Exactly the kind of measurement that determines how dangerous an incoming storm will be. It also carries a compact coronagraph instrument, specifically built to detect coronal mass ejections as they form and depart the Sun. It represents the first satellite that this agency has dedicated entirely to continuous, operational space weather monitoring, rather than treating the task as a secondary function of a broader science mission. Alongside that dedicated space weather satellite, NASA has also stationed a spacecraft called the Interstellar Mapping and Acceleration Probe at the same L1 location. Its mission focuses on deepening our understanding of how space storms develop, evolve, and eventually dissipate. Work intended to improve preparedness for future space weather events by supplying continuous, real-time observations of the solar wind as it streams past. The European Space Agency is planning to push this early warning concept even further with a mission called Vigil, scheduled to launch in 2031, rather than sitting at the L1 point directly between Earth and the Sun. Vigil will be positioned at the L5 Lagrange point, off to one side of the direct Earth-Sun line. From that unique vantage point, it will be able to observe active regions on the Sun's surface as they rotate into view, before those regions ever face directly toward Earth, potentially extending our warning time for incoming space, whether from a matter of minutes to as much as several days, on the ground. Meanwhile, engineers and grid operators are working to reduce the risk of blackouts and communication failures the next time a truly severe solar storm arrives. This includes deploying smart grid technologies and high-voltage surge protection equipment throughout power transmission networks, establishing strategic reserves of spare transformers, so damaged infrastructure can be replaced quickly rather than waiting months for custom-manufactured replacements, and researching new shielding materials, including Faraday cage-style enclosures for sensitive electronic components, designed to deflect the electromagnetic pulses that a severe storm can induce, to really appreciate why this current cycle has proven so scientifically important. It helps to step back and look at the long history of sunspot observation, because it turns out the Sun does not always behave with clockwork regularity. Systematic sunspot records stretch back centuries, and buried within them is a genuinely strange episode called the Maunder Minimum, spanning roughly from 1645 to 1715. During this 70-year stretch, sunspots became extraordinarily rare, with some years showing almost no spots at all, even though observers of the era were actively looking for them. This period coincided with an especially cold stretch of European and North American climate, sometimes called the Little Ice Age. And while scientists are careful not to claim solar activity was the sole cause of that cooling, the correlation between a quiet sun and a colder climate remains one of the more intriguing open questions in solar climate science. It also demonstrates something important. The 11-year cycle we now consider standard has not always held with perfect regularity, and the mechanisms driving longer-term variations in solar behavior are still not fully understood. Sunspots themselves follow patterns that took decades of careful observation to untangle. In the early 20th century, the American astronomer George Ellery Hale discovered that sunspots carry strong, measurable magnetic fields, and that pairs of spots within the same active region consistently show opposite magnetic polarity, one behaving like a North Pole and the other like a South Pole. He further discovered that this polarity pattern flips completely from one 11-year cycle to the next, which is precisely the 22-year Hale cycle mentioned earlier in connection with solar orbiters' polar observations. A related pattern, known as Joy's law, describes how the leading sunspot in a pair tends to sit slightly closer to the solar equator than the trailing spot, with the tilt angle increasing at higher solar latitudes, a subtle geometric signature of the same underlying dynamo process that generates the spots in the first place. If you plot the latitude at which sunspots appear over the course of many cycles, you get a distinctive pattern that solar physicists nicknamed the butterfly diagram, because the resulting shape resembles a series of butterfly wings repeating across time. At the start of each cycle, new sunspots emerge at relatively high latitudes, farther from the solar equator, as the cycle progresses toward its maximum and then declines. The average latitude of new sunspots gradually drifts closer and closer to the equator, before the pattern resets and a new cycle begins spawning spots at high latitude again. This migration pattern is intimately connected to the same poleward flux transport process that the polar field precursor forecasting method depends on, the same process that solar orbiters' 2025 findings suggested may be running faster than expected during the current cycle. Understanding exactly why the strength and timing of these cycles varies so much from one to the next remains one of the biggest open questions in solar physics. Some cycles, like cycle 19 back in the 1950s, produced sunspot counts far higher than anything seen in the modern era. Others, like the recent cycle 24, were remarkably quiet by comparison. Explaining this variability convincingly is part of why the debate between the deep tachocline dynamo model and the newer near-surface dynamo model described earlier matters so much. A model that can only reproduce an average generic solar cycle is far less useful to forecasters than one capable of explaining why specific cycles turn out unusually strong or unusually weak, which is exactly the kind of test the magneto-rotational instability model is now being subjected to, using data gathered by missions like Parker Solar Probe and Solar Orbiter. It is also worth understanding the physical structure of the Sun itself, since so much of this story depends on exactly where inside the star different processes take place. At the very center lies the core, where immense pressure and temperature, reaching around 15 million degrees Celsius, drive the nuclear fusion reactions that power the entire star, converting hydrogen into helium and releasing the energy that eventually makes its way to the surface. Surrounding the core is the radiative zone, a region so dense that individual photons of light can take many thousands of years to random walk their way outward through it, constantly being absorbed and re-emitted by the surrounding plasma. Above the radiative zone sits the convective zone, the outer layer where plasma becomes buoyant enough to physically rise, cool, and sink in continuous convective currents, similar in principle to boiling water, and it is within and around this convective zone, at either the tachocline boundary beneath it or the newly proposed shallower layer near its outer edge, that the solar dynamo is thought to operate. Above the visible surface, called the photosphere, sits the thin, relatively cool chromosphere, and above that, the much hotter, far more extended corona, the layer whose extreme temperatures Parker Solar Probe has helped explain through the switchback and reconnection mechanisms described earlier. The corona in turn extends outward into interplanetary space as the solar wind, a continuous outflow of charged particles that streams past every planet in the solar system and ultimately inflates the heliosphere, the vast magnetic bubble that separates our solar system from interstellar space. The very existence of a continuously flowing solar wind was itself a controversial prediction when Eugene Parker first proposed it mathematically in 1958. Many of his contemporaries doubted that the Sun could sustain a continuous outward flow of plasma at all, and it took direct spacecraft measurements taken in the early 1960s to finally confirm that the solar wind was real, a vindication that, decades later, would be echoed by the same researchers' ideas about coronal heating, being confirmed by a probe built in his honor. Beyond the heliosphere itself, spacecraft like the two Voyager probes, launched in the 1970s, have carried instruments that eventually crossed into true interstellar space, providing direct measurements of where the solar wind's influence finally gives way to the surrounding galactic environment. Those crossings, which occurred decades into each spacecraft's mission, help define just how large a bubble our Sun's magnetic influence actually carves out of the surrounding galaxy, and they provide an important boundary condition for models of how solar activity including the very storms discussed throughout this look at cycle 25, ultimately propagates and dissipates as it moves outward from its source, back closer to home. It is worth understanding a bit more about how Earth's own magnetic environment responds to all of this incoming solar activity, since that response is what actually determines the real-world consequences of a storm. Earth's magnetosphere is shaped like a comet, compressed on the side facing the sun by the constant pressure of the solar wind, and stretched out into a long tail on the side facing away from the sun. Where the solar wind first encounters this magnetic bubble, it forms a standing shock wave called the bow shock, somewhat analogous to the shock wave that forms in front of a supersonic aircraft. Except here, the supersonic flow is a stream of charged particles rather than air. Just inside the bow shock lies a turbulent boundary region called the magnetosheath, where solar wind plasma is slowed, heated, and deflected around the main body of the magnetos. Trapped within the inner magnetosphere are the Van Allen radiation belts, two donut-shaped regions of highly energetic charged particles held in place by Earth's magnetic field. These belts can swell dramatically in both size and particle energy during geomagnetic storms, posing additional radiation hazards to satellites that pass through or near them, and their behavior is closely monitored by dedicated radiation belt research missions precisely because of how sensitive they are to exactly the kind of solar activity driving the current. Unusually strong cycle. Scientists and forecasters use a couple of standardized scales to communicate just how severe a given geomagnetic storm actually is, since a raw description of magnetic field strength does not mean much to the public or even to many engineers managing vulnerable infrastructure. The most common of these is called the KP index, a scale running from 0 up to 9, derived from magnetometer readings collected at observatories scattered around the world, which quantifies disturbances in Earth's magnetic field over 3-hour intervals. Layered on top of this is what is often called the G scale, running from G1, described as minor, up to G5, described as extreme, used specifically to communicate the practical impact of a storm on things like power grids, satellite operations, and radio communications. The May 2024 storm reached G5, the maximum extreme classification, the first time that threshold had been reached since a storm back in 2003, underscoring just how unusual this particular Cycle 25 event turned out to be. Looking back through the historical record of major geomagnetic storms puts the current cycle into useful context. In March of 1989, a severe geomagnetic storm induced powerful currents in the power grid serving Quebec, Canada, triggering a cascading series of equipment failures that plunged the entire province into a blackout lasting roughly 9 hours and affecting millions of people. A vivid demonstration of how vulnerable modern electrical infrastructure can be to space weather, even without an event on the scale of the Carrington event. In late October and early November of 2003, a series of intense solar flares and coronal mass ejections, an episode now often referred to as the Halloween storms, disrupted satellites, forced airlines to reroute polar flights to avoid radiation exposure for crew and passengers, and even damaged instruments aboard some spacecraft, including a temporary loss of function on an instrument aboard the Mars Odyssey orbiter, illustrating that these effects are not confined to the immediate vicinity of Earth alone. Further back, in August of 1972, a powerful solar storm swept through space in the gap between NASA's Apollo 16 and Apollo 17 missions, missing an active crewed lunar mission by only a few months. Had astronauts been on the lunar surface or in transit during that particular storm, they would likely have received a dangerous, and potentially lethal radiation dose. A sobering reminder of just how much timing matters when it comes to protecting crews traveling beyond Earth's protective magnetic field, and one that continues to inform how mission planners think about scheduling extravehicular activities and lunar surface excursions during periods of heightened solar activity. Even today, these historical events help explain why agencies like the Space Weather Prediction Center, operated by the National Oceanic and Atmospheric Administration, exist as dedicated forecasting bodies in the first place, issuing regular alerts and watches for solar flares, geomagnetic storms, and radiation storms in much the same way meteorological agencies issue forecasts and warnings for terrestrial weather. Their forecasts increasingly draw on exactly the kind of data streams described earlier in this discussion. Polar field measurements from instruments like the helioseismic and magnetic imager, real-time solar wind readings from spacecraft stationed at the L1 Lagrange point, and eventually, once it launches, the extended early warning capability that the Vigil mission is expected to provide from its vantage point at L5, as human spaceflight ambitions extend further from Earth, particularly with NASA's Artemis program aiming to establish a sustained presence on the Moon and eventual crewed missions toward Mars. The stakes attached to understanding and forecasting solar activity only grow larger. A lunar surface mission lacks the protective benefit of Earth's thick atmosphere entirely, and a mission traveling to Mars would spend many months in the open radiation environment of interplanetary space, far beyond the reach of Earth's magnetosphere for the vast majority of the journey. Radiation shielding strategies for these future missions, along with the kind of onboard radiation monitoring systems already demonstrated on Artemis II, depend directly on having accurate, timely forecasts of when a dangerous solar event might occur, which in turn depends on exactly the kind of fundamental science described throughout this discussion of Cycle 25. There is another entire line of evidence that helps put modern solar storms into perspective, one that does not come from satellites or telescopes at all, but from tree rings and ice cores. When a sufficiently energetic solar particle event strikes Earth, it can trigger a measurable spike in the production of certain rare isotopes in the atmosphere, particularly carbon-14 and beryllium-10, which then become locked into the growth rings of trees or the layered ice of polar ice sheets, effectively creating a natural, continuous recording instrument that has been running for thousands of years. In 2012, a Japanese researcher named Fusa Miyake identified an enormous spike in carbon-14 concentration in a Japanese cedar tree corresponding to the year 774. A spike far too large to be explained by any solar event observed in the modern era since that initial discovery. Researchers have identified several more of these extreme events scattered throughout the historical tree ring and ice core record, now generally referred to as Miyake events in her honor, with additional confirmed spikes traced to around the year 660 and around the year 993, among others. What makes these Miyake events so scientifically important is that they appear to represent solar particle events dramatically more powerful than anything humanity has directly observed, with modern instruments potentially many times stronger even than the Carrington event of 1859. If an event of that scale were to strike modern Earth, the consequences for satellites, power grids, and aviation could be severe enough to dwarf even the most pessimistic Carrington-scale damage estimates discussed earlier. Because we still do not fully understand what triggers events of this magnitude, or how frequently they might recur, some researchers argue that current space, weather preparedness, planning, largely built around Carrington-scale worst-case scenarios, may actually be underestimating the true tail risk posed by the most extreme end of solar activity. This uncertainty is itself part of why continued investment in solar physics research, of exactly the kind driving the Parker Solar Probe and Solar Orbiter missions, matters so much, since a better understanding of the underlying dynamo mechanism could eventually help clarify how likely truly extreme events are to occur within any given human lifetime. Zooming out even further, astronomers have also begun studying magnetic activity cycles on other sun-like stars, using long-duration brightness monitoring missions originally designed to hunt for exoplanets, such as the Kepler and TESS space telescopes. Subtle, periodic dimming and brightening patterns in a star's light, caused by star spots analogous to sunspots rotating in and out of view, allow researchers to estimate the length and strength of magnetic cycles on stars other than our own. These studies have found considerable diversity among sun-like stars, some showing cycles considerably shorter or longer than our sun's 11-year rhythm, and some showing magnetic activity levels dramatically higher than anything our own star has displayed in recorded history. This broader stellar context helps researchers understand where our sun sits within the overall range of behavior possible for a star of its type, mass, and age, and offers additional data points for testing whether dynamo models developed for our own sun, including the newly proposed near-surface magneto-rotational instability-driven mechanism, might generalize to explain magnetic cycles on other stars as well. It is also worth digging a little deeper into exactly why auroras appear at all, and why a strong storm can push them so much farther from the poles than usual. Auroras form when charged particles, mostly electrons, are accelerated along Earth's magnetic field lines and funneled down into the upper atmosphere near the polar regions. As these energetic particles collide with atoms and molecules of oxygen and nitrogen high in the atmosphere, they transfer energy into those atoms, briefly exciting their electrons into a higher energy state. When those electrons drop back down to their normal resting state, they release that stored energy as a photon of light, producing the shimmering, colored glow we recognize as an aurora. The specific color produced depends on which gas is excited and at what altitude. Oxygen atoms tend to produce the familiar green glow at lower altitudes and a rarer red glow at higher altitudes, while nitrogen tends to contribute blue and purple hues under normal, quiet conditions. This entire process is confined to a narrow ring around each magnetic pole called the auroral oval, generally sitting at high latitudes far from most population centers. During a major geomagnetic storm, though, the increased energy and particle flux pouring into the magnetosphere expands this auroral oval dramatically, pushing its equatorward edge much farther from the poles than usual. This is exactly why the May 2024 storm produced auroras visible from Florida and the Caribbean, locations that almost never see this phenomenon under ordinary conditions, and why the storm ranks among the most geographically widespread auroral displays documented in centuries. Geomagnetic storms also have a less visually dramatic but practically important effect on Earth's upper atmosphere, one that connects directly back to the satellite risks described earlier. The layer of atmosphere where most low Earth orbit satellites operate, called the thermosphere, physically heats up and expands during a geomagnetic storm. As energy from the solar wind pours into it, this expansion increases atmospheric density at a given altitude, which in turn increases atmospheric drag on any satellite passing through that region. Increased drag causes satellites to lose orbital altitude faster than normal, requiring more frequent adjustment maneuvers to stay in their intended orbit, a challenge that even affects large, well-monitored structures like the International Space Station, which periodically requires reboost maneuvers to counteract natural orbital decay. a need that becomes noticeably more urgent during periods of high solar activity, like the current cycle 25 maximum. For the thousands of small commercial satellites that make up modern low Earth orbit constellations, many of which lack the fuel reserves or maneuvering capability of a large crewed station, this kind of unplanned orbital decay poses a genuine operational risk, and a small number of satellites from at least one major commercial constellation have previously been lost entirely, after being deployed into an atmosphere unexpectedly, puffed up by a geomagnetic storm shortly after launch. Beyond satellites and power grids, geomagnetic storms and the solar flares that often precede them also interfere directly with radio communication, particularly the high-frequency radio bands used for long-distance communication by aircraft, ships, and emergency services in remote regions without reliable satellite coverage. Intense solar flares release a burst of X-ray and extreme ultraviolet radiation that reaches Earth in a matter of minutes, well ahead of any accompanying coronal mass ejection. And this radiation can suddenly increase ionization in the lower ionosphere on the sunlit side of the planet, causing high-frequency radio signals to be absorbed rather than reflected as they normally would be. This produces what forecasters call a radio blackout, a sudden and often complete loss of high-frequency communication capability across the sunlit hemisphere, lasting anywhere from several minutes to a few hours depending on the intensity of the flare, and representing yet another practical consequence of solar activity that operators of transoceanic flights and remote research stations have to plan around. Finally, increased solar activity has an interesting and somewhat counterintuitive protective effect when it comes to a different kind of radiation entirely: galactic cosmic rays arriving from far outside our solar system. These extremely energetic particles, originating from sources like distant supernova remnants, constantly bombard the solar system from all directions. But the sun's own magnetic field and the outward flowing solar wind act as a kind of shield, deflecting and scattering a portion of these incoming cosmic rays before they can reach the inner solar system. During periods of high solar activity, this shielding effect strengthens, temporarily reducing the flux of galactic cosmic rays reaching Earth and nearby space, a phenomenon researchers can observe directly as sudden dips in cosmic ray detector readings following a major solar event, known as Forbush decreases, named after the physicist Scott Forbush, who first documented the effect in the 1930s. This means that, somewhat paradoxically, the same active sun capable of producing dangerous solar particle events and damaging geomagnetic storms also temporarily reduces the background level of a completely different kind of space radiation, one more relevant to long-duration crewed missions traveling far from Earth, illustrating just how many interconnected radiation environments astronauts and spacecraft designers ultimately have to account for, given how central the helioseismic and magnetic imager has been throughout this story, both as the instrument that enabled the original polar field forecasting method and as the instrument later found to be undercounting the true polar field strength. It is worth understanding a little more about how it actually works, and why measuring the sun's magnetic field is such a fundamentally difficult task in the first place. The instrument does not measure magnetism directly the way a laboratory magnetometer might. Instead, it relies on a technique called the Zeeman effect, in which a magnetic field splits certain spectral lines, the specific wavelengths of light absorbed or emitted by atoms, into multiple closely spaced components. By precisely measuring the separation and polarization of these split spectral lines in light coming from the sun's surface, scientists can infer both the strength and the orientation of the magnetic field present at that location. This is an extraordinarily delicate measurement, even under ideal conditions, and it becomes considerably harder near the sun's poles, where the instrument is viewing the relevant magnetic field lines at a steep, nearly edge on angle from Earth's vantage point, rather than looking straight down on them, which likely contributed to the systematic underestimate later uncovered by the National Solar Observatory's simulation work, the same spacecraft carrying this magnetic image. The Solar Dynamics Observatory also carries an instrument dedicated to a completely different technique called helios, which uses the same underlying imager but applies it to a different purpose, tracking sound waves that ripple across the sun's surface. These waves are generated by the constant churning of convective plasma just beneath the surface, and as they propagate, they cause the visible surface to oscillate up and down in complex, overlapping patterns, somewhat like the surface of a drum vibrating after being struck, except with millions of overlapping frequencies rather than a single note. By carefully analyzing how these surface oscillations behave, and how the underlying sound waves are refracted and altered as they pass through different layers of the solar interior, scientists can effectively build up an indirect picture of conditions deep inside the sun, including the temperature, density, and rotation rate at different depths, all without ever directly seeing beneath the visible surface. This technique was instrumental in first identifying the Tachak line as a boundary layer, where the sun's rotation rate changes abruptly with depth, providing much of the original observational foundation for the classic dynamo theory later challenged by the 2024 supercomputer simulations described earlier. Complementing the Solar Dynamics Observatory's view from near Earth, NASA's twin stereo spacecraft, launched in 2006, were placed into orbits that gradually drifted ahead of and behind Earth along its orbital path around the Sun, eventually providing, for a period, a genuinely three-dimensional, stereoscopic view of solar activity, similar in principle to how two eyes spaced apart allow the human brain to perceive depth. This stereoscopic capability proved especially valuable for tracking coronal mass ejections as they left the Sun and traveled through interplanetary space, since a single vantage point from directly between the Sun and Earth struggles to judge whether an ejection is heading directly at Earth or off to one side. A critical piece of information for accurately forecasting whether a given eruption poses any real threat at all. Instruments called coronagraphs carried aboard stereo and several other solar missions work by using a physical disk to block out the overwhelmingly bright light of the solar surface itself, similar to how the moon blocks the sun during a total solar eclipse, allowing the comparatively faint corona and any material erupting from it to be observed and tracked clearly. Against the darkened background, it is easy to think of global navigation satellite systems purely in terms of driving, directions, or mapping applications, but their importance to modern infrastructure runs far deeper than that, which is part of why the GPS disruptions during the May 2024 storm were treated as such a serious concern by regulators and industry alike. These satellite constellations broadcast an extraordinarily precise timing signal, derived from atomic clocks accurate to within a few billionths of a second, and that timing signal has quietly become a foundational utility for numerous systems that have nothing to do with navigation at all. Financial markets rely on satellite-derived timestamps to synchronize high-speed trading systems and to establish a legally verifiable, consistent order of transactions across different exchanges. Electrical power grids use the same timing signals to synchronize the phase of alternating current across widely separated substations, a synchronization that becomes especially important precisely during the kind of grid stress event that a geomagnetic storm can also trigger. Cellular telephone networks and data centers rely on this timing to coordinate the handoff of signals between towers and to keep distributed computing systems properly synchronized, modern precision agriculture equipment, automated shipping and logistics tracking, and emergency response coordination systems all quietly depend on the same underlying signal. This is precisely why the position errors, data gaps, and tracking failures documented across European airspace during the May 2024 storm drew so much attention from aviation regulators and infrastructure planners. Not because a temporary disruption to any single flight was itself catastrophic, but because it served as a visible, concrete demonstration of how a moderately severe storm, one considerably weaker than a full Carrington-scale event, could already meaningfully degrade systems that a great deal of modern life quietly assumes will simply always work. It is one of the clearer illustrations of why continued investment in space weather forecasting is not merely an academic exercise for solar physicists, but a practical necessity closely tied to the resilience of the systems modern economies depend on every single day, given everything scientists have learned over the course of this single unusually active cycle. Attention naturally turns toward what comes next. Cycle 26 is expected to begin sometime between the years 2029 and 2032, following the same kind of solar minimum transition period that has preceded every recorded cycle before it. Forecasting its eventual strength will draw on the very same polar field precursor method used for Cycle 25, but this time armed with a considerably better understanding of the pitfalls involved. Researchers will need to account for the newly discovered calibration limitations of instruments like the helioseismic and magnetic imager, potentially correcting past and future measurements to better reflect the true polar field strength rather than the apparently undercounted values recorded throughout much of Cycle 25. They will also need to incorporate the possibility of a shallower, near-surface dynamo operating through magneto-rotational instability, a mechanism that may respond to different physical drivers than the deep Tachak line model long assumed to govern cycle-to-cycle variability. And they will need to factor in solar orbiters finding that poleward flux transport may be moving faster than older models assumed, a correction that could meaningfully shift forecasts for Cycle 26's eventual strength even before the Sun reaches its next minimum. A natural question to ask at this point is why a calibration limitation as significant as undercounting half of the Sun's true polar magnetic field strength went unnoticed for so long, given that the helioseismic and magnetic imager had already been operating for well over a decade by the time the discrepancy was identified. Part of the answer lies in the nature of the problem itself. Instrument calibration errors of this kind are often extremely difficult to detect using only the instrument's own data, precisely because there is no independent, equally precise measurement of the same quantity available for comparison. Scientists generally have to infer that something is wrong indirectly, often only after accumulating enough real-world evidence. In this case, an entire solar cycle that behaved very differently than the instrument's own data predicted. That something in the measurement chain must be off. Only then does it become worthwhile to invest the considerable effort required to build a detailed virtual simulation of the instrument itself and test it against synthetic data with precisely known properties. Exactly the approach the National Solar Observatory team eventually took. This is a useful reminder that even mature, well-validated scientific instruments can harbor subtle systematic errors that remain hidden until a sufficiently unusual real-world event forces researchers to go back and rigorously check their assumptions, resolving the deeper question of exactly where the solar dynamo actually operates, whether at the traditional Tachak line depth or at the shallower layer, suggested by the 2024 supercomputer simulations. will likely require a combination of approaches working together rather than any single decisive measurement. Continued helioseismology data from missions like the Solar Dynamics Observatory can help probe conditions at both candidate depths with ever-increasing precision as data accumulates over additional cycles. Direct in-situ measurements from Parker Solar Probe, sampling the near-surface magnetic environment directly as it makes ever closer approaches over the remainder of its mission, can provide observational tests that a purely theoretical model cannot. And Solar Orbiter's unprecedented polar vantage point offers an entirely new category of data: direct imaging and spectroscopy of the polar regions, where both candidate dynamo models make somewhat different predictions about the detailed structure and evolution of the polar magnetic field over the course of a cycle. It is also worth noting that professional research missions are not the only source of solar data feeding into this ongoing scientific effort. A worldwide network of amateur and citizen astronomers, using relatively modest telescopes equipped with proper solar filters, continues to contribute daily sunspot counts and observations to organizations that maintain long-term sunspot records, carrying on a tradition of citizen contribution to solar science that stretches back to the earliest systematic sunspot counters in the 1800s. These contributions help fill in observational gaps between professional satellite passes and provide an important independent cross-check against the automated counting algorithms used by space-based instruments. A small but meaningful example of how a genuinely global, multi-generational effort spanning professional space agencies, university research teams, and dedicated amateur observers alike continues to refine our understanding of the star that makes life on Earth possible in the first place, and a reminder that not every meaningful scientific contribution requires a billion-dollar spacecraft to make. Looking at the full sweep of what Cycle 25 has revealed, it becomes clear that this was never simply a story about one unexpectedly strong solar maximum. It became, almost by accident, a stress test for an entire framework of assumptions solar physicists had built up over more than a century of study. Assumptions about where the dynamo lives, how reliably we can measure the polar fields that feed our forecasts, and what the poorly understood polar regions of our nearest star are actually doing while turned away from direct observation for the vast majority of space exploration history. Each of the missions described throughout this discussion, the Solar Dynamics Observatory sitting in Earth orbit, the Parker Solar Probe diving repeatedly through the corona itself, and the Solar Orbiter finally tilting its view up and over the solar poles, contributed a distinct and complementary piece of a puzzle that, even now, is not fully assembled. Solar cycles also have subtler effects that reach beyond the dramatic storm events discussed so far. Effects that researchers have spent decades carefully measuring and disentangling from other influences. Total solar irradiance, essentially the overall brightness of the sun as measured from a fixed distance, varies slightly across the solar cycle, generally running a few tenths of 1% higher at solar maximum than at solar minimum, driven by the balance between dark, relatively cool sunspots, which locally reduce brightness, and bright surrounding regions called faculae, which more than compensate for that reduction when the sun is magnetically active. Climate researchers have studied this variation extensively using long-running satellite radiometers, and the scientific consensus is that while this small brightness fluctuation does measurably affect the very upper layers of Earth's atmosphere and can be detected in careful long-term climate records, it is far too small in magnitude to serve as a significant driver of the warming trend observed over the past century, a conclusion supported by numerous independent lines of evidence in the broader climate science literature. This distinction matters because popular discussion sometimes conflates dramatic, headline-grabbing solar storm activity of exactly the kind driving this particular cycle's unusual strength, with the comparatively tiny and well-quantified brightness variation relevant to long-term climate trends. Two genuinely different phenomena operating on very different scales and timelines. On a considerably lighter note, solar activity has long been closely watched by an entirely different community for entirely different reasons. Amateur radio operators, high-frequency radio signals, the same frequency bands vulnerable to sudden radio blackouts during intense solar flares described earlier, also depend heavily on the ionosphere for long-distance propagation under normal circumstances, since these signals bounce off ionized layers of the upper atmosphere to travel far beyond the horizon, rather than simply traveling in a straight line into space. A more active sun generally means a more strongly ionized upper atmosphere, which, outside of the disruptive extremes of a major flare or storm, can actually improve long-distance, high-frequency radio propagation considerably, allowing amateur operators to make contact with far more distant stations than would be possible during a quiet solar minimum. This is one of the more accessible, hands-on ways that ordinary people around the world have directly experienced the practical effects of the current, unusually active solar cycle, alongside the more widely reported aurora sightings, simply by noticing that their radio equipment seemed to be reaching farther than usual. The broader study of stellar magnetic activity, mentioned earlier in the context of Kepler and TESS, observations of other sun-like stars, turns out to connect to yet another major area of modern astronomy, the search for potentially habitable worlds around other stars. Many of the most promising nearby targets for detecting Earth-sized exoplanets are red dwarf stars, which are smaller, cooler, and far more numerous throughout the galaxy than sun-like stars, but which also tend to exhibit dramatically more intense and more frequent flaring activity relative to their overall size. A planet orbiting closely enough to a red dwarf to receive Earth-like levels of warmth sits so close to its host star that even a moderately powerful flare can bathe that planet in a dose of ultraviolet and X-ray radiation vastly larger, relative to background levels, than anything Earth experiences even during the most severe storms described throughout this discussion. Understanding exactly how a star's magnetic cycle behaves, how frequently it produces damaging flares, and how effectively a planet's own atmosphere and magnetic field might shield its surface from that activity, has become an essential consideration for astrobiologists trying to assess which of the many newly discovered exoplanets might realistically support conditions favorable to life. In this sense, the detailed physical mechanisms uncovered by missions studying our own sun, the near-surface dynamo model, the switchback-driven coronal heating process, and the complex polar magnetic behavior revealed by Solar Orbiter, all feed into a much larger scientific effort to understand what makes any star, anywhere in the galaxy, a safe or dangerous host for a potentially habitable planet. Stepping back to consider the practical value of the research described throughout this discussion, it is worth weighing the relatively modest cost of missions like Parker, Solar Probe, Solar Orbiter, and the various L1 and L5 monitoring satellites against the scale of economic damage a single, severe, poorly forecast geomagnetic storm could inflict. The combined cost of building, launching, and operating this entire generation of solar observation missions runs to a few $1 billion spread across multiple space agencies and many years. A substantial sum in absolute terms, but one that pales next to even the low end of the $600 billion to $2.6 trillion damage estimate associated with a single unmitigated Carrington-scale storm striking the United States alone. Every additional minute of reliable warning time that missions like the planned Vigil spacecraft can provide, extending advance notice from a scant 15 to 60 minutes up toward several days, translates directly into meaningfully more time for grid operators to take protective measures, for airlines to reroute polar flights, and for satellite operators to place vulnerable spacecraft into safer configurations, all of which can substantially reduce the eventual damage from an otherwise unavoidable natural event. One more puzzle worth mentioning is the sheer size of the swing between cycle 24, the weakest maximum in roughly 100 years, and cycle 25, which ended up nearly double its own original forecast. Such a dramatic reversal from an unusually quiet cycle straight into an unusually vigorous one does not fit comfortably into a simple picture where each cycle's strength depends only on gradual, gently evolving conditions carried over from the one before it. Some researchers have suggested that the transition itself, the process by which one cycle's declining sunspot activity gives way to the next cycle's high-latitude emergence, may involve more complex, possibly chaotic dynamics than the relatively smooth polar field precursor model captures on its own. Something that could help explain both the depth of cycle 24's weakness and the strength of cycle 25's rebound as connected outcomes of the same underlying transition, rather than two independent, unrelated events. Because of uncertainties like this, solar physicists monitoring the eventual approach of solar minimum and the onset of cycle 26 will be watching for several specific, well-defined signals rather than waiting passively for sunspot counts to simply start rising again. One key indicator is the appearance of the very first high-latitude sunspots carrying the reversed magnetic polarity associated with the new cycle, emerging even while the old cycle's low-latitude spots are still fading away. A signature clearly visible in the butterfly diagram pattern described earlier, and one of the most reliable early markers that a new cycle has technically begun beneath the surface even before its activity becomes visually obvious. Another is the continued tracking of polar field strength itself, now presumably corrected for the calibration issue identified in the helioseismic and magnetic image. Watching closely to see whether the polar fields building up toward the coming minimum look unusually strong, unusually weak, or roughly typical compared to the historical record, keeping in mind the added twist that solar orbiters' 2025 findings suggest this poleward migration process itself may now need to be modeled as happening faster than researchers previously assumed. All of this adds up to a genuinely exciting moment in solar physics, one where several independent missions, built for somewhat different purposes and operated by different space agencies, have converged to reveal that a star humans have studied since Galileo first pointed a telescope at it still holds fundamental secrets. We are only now developing the tools to properly investigate. The next several years, as cycle 25 winds down and cycle 26 begins to stir, will offer a genuine test of whether the lessons learned this time around, the corrected instrument calibrations, the reconsidered dynamo depth, and the faster than expected poleward flux transport, actually translate into meaningfully better forecasts, or whether the sun still has a few more surprises in store that no current model fully anticipates. What remains clear is that our nearest star, despite centuries of dedicated study and an increasingly sophisticated fleet of spacecraft trained on it from every conceivable angle, is still capable of surprising the researchers who study it most closely. The gap between a forecast of 115 sunspots and an observed peak of 216 was not just a miss. It was a signal that something in our basic picture of how the sun generates and organizes its magnetic field needed to be revisited, and the ensuing investigation has genuinely reshaped several long-standing assumptions in the field. Whether the near-surface dynamo model ultimately holds up against further testing, whether the corrected polar field measurements bring future forecasts back in line with reality, and whether the faster poleward migration observed by solar orbiter turns out to be a permanent feature of the Sun's behavior or a temporary quirk of this particular cycle, are all questions that current and upcoming missions are actively working to answer. Each new orbit of Parker's solar probe, each further tilt of solar orbiter's vantage point toward the poles, and each fresh set of measurements from the newly arrived L1 monitoring satellites adds another piece to a puzzle that, after more than 4 centuries of observation, our Sun is still only slowly giving up. It is worth remembering, too, that essentially none of this research happens in isolation. Solar physics sits at an unusual crossroads within the broader scientific enterprise, drawing simultaneously on plasma physics, fluid dynamics, high-performance computing, spectroscopy, and increasingly on the same kind of large-scale statistical and machine learning techniques used in fields as varied as genomics and particle physics. Since sifting through the volume of data produced by instruments like the helioseismic and magnetic imager or the Parker solar probe's suite of particle detectors requires computational tools that did not exist even 20 years ago. The National Solar Observatory's discovery of the instrument's calibration shortfall, for example, depended on being able to construct and run a sufficiently detailed virtual simulation of the entire measurement chain, a task that would have been computationally out of reach for earlier generations of researchers working the same problem with the same fundamental physics questions in mind. In much the same way, the 2024 supercomputer simulations that first suggested a shallower dynamo location required access to some of the most powerful computing resources in the world, resources that have only become available to solar physicists relatively recently as national laboratories have made high-performance computing time increasingly available to basic research programs outside of fields like weapons design or climate modeling that have traditionally dominated supercomputer allocation. This cross-disciplinary dependence also means that continued progress in understanding our Sun is closely tied to broader trends in scientific infrastructure and international collaboration. Missions like Solar Orbiter represent a genuine partnership between the European Space Agency and NASA, combining European-built spacecraft and instrumentation with American launch capability and mission operations support, while data from Japan's Array satellite, originally designed primarily to study Earth's radiation belts, ended up providing some of the most important direct evidence linking negative ionospheric storms to delayed plasmasphere recovery, a scientific payoff that likely would not have been possible without open, cooperative data-sharing agreements between space agencies that do not always make headlines, but that quietly underpin a great deal of modern space science. Every one of the specific discoveries traced through this discussion, the corrected polar field measurements, the reconsidered dynamo depth, the switchback-driven coronal heating mechanism, the mixed polarity south pole, and the negative ionospheric storm mechanism delaying plasmasphere recovery, ultimately depended on this same kind of quiet, sustained, and often underappreciated international scientific cooperation carried out over years and even decades. Long before any single dramatic storm made headlines and drew public attention to why any of it mattered in the first place, there is a certain irony worth sitting with, that a star sitting only about 8 light minutes away, close enough that its light reaches Earth faster than most people can finish reading a single paragraph, and studied continuously by dedicated instruments for well over a century, could still contain surprises capable of catching an entire scientific community off guard as recently as this current cycle. Compare that to the many far more distant objects astronomers study using nothing but faint light gathered over years of patient observation, and the sun's proximity might seem like it should make solving mysteries like these considerably easier. In some ways it does. No other star can be studied with anything close to the resolution. The direct in situ sampling, or the sheer instrumental redundancy that missions like the Solar Dynamics Observatory, Parker's Solar Probe, and Solar Orbiter collectively bring to bear on our own sun. Yet in other ways, that very proximity introduces its own complications. Since a star studied this closely reveals layers of genuine complexity, tangled magnetic fields, unexpectedly located dynamos, subtly miscalibrated instruments, and asymmetric polar behavior that would likely remain completely invisible when observing a star light years away using only its integrated brightness and the sparse, distant technique of monitoring how its light dims when a companion planet transits in front of it. This tension between the Sun as the most thoroughly studied star in the universe and the Sun as a continuing source of genuine scientific surprise is really what makes Cycle 25 such a compelling case study in how modern science actually progresses. It rarely moves in a single, smooth line from ignorance directly to certainty. Instead, it tends to advance through exactly this kind of episode. An anomaly appears. In this case, a solar maximum that overshot its forecast by a wide margin. Existing instruments and theories get scrutinized more carefully than they otherwise would have been. A previously unnoticed calibration flaw and a previously underappreciated dynamo mechanism both come to light as a result, and the overall picture of how the system works becomes measurably more accurate, while simultaneously revealing new questions that are slightly less curious, slightly less well-instrumented research community might never have thought to ask in the first place. Multiply that pattern across the many other open questions still surrounding our sun. The true frequency of Miyake-scale extreme events, the precise mechanism driving the surprising speed of poleward flux migration, and the reasons behind the dramatic swing from Cycle 24's historic weakness to Cycle 25's unexpected strength. And it becomes clear that this single video has really only scratched the surface of an area of science that remains very much a work in progress, with genuinely new discoveries likely to keep arriving for as long as instruments keep watching. It is genuinely rare for a single research area to see this many independent lines of evidence: an instrument recalibration, a supercomputer simulation, and two entirely different spacecraft approaching the problem from two entirely different vantage points converge on the same broad conclusion within the space of just a couple of years. And that convergence itself is part of why solar physicists have described this particular cycle as an unusually productive one scientifically, even setting aside the risks and disruptions it caused here on Earth. And it is worth remembering that almost everything discussed here, the corrected view of the polar field precursor method, the possibility of a shallow, near-surface dynamo, the switchback mechanism heating the corona to millions of degrees, the tangled dual polarity chaos briefly present at the sun's south pole, and the negative ionospheric storm mechanism that kept Earth's plasmasphere depleted for 4 extra days, was essentially unknown or only weakly suspected as recently as 5 years ago. That pace of discovery, compressed into such a short window and driven by a combination of a single, unusually strong solar maximum and a small fleet of remarkably capable spacecraft finally positioned to observe it properly, suggests that the coming decade of solar research, spanning the tail end of Cycle 25, the quiet transition through the next solar minimum, and the eventual rise of Cycle 26, is likely to keep delivering discoveries just as significant as the ones covered throughout this discussion. Whether or not the next maximum turns out to be anywhere near as dramatic as this one, none of this diminishes how much has already been settled about our star since Galileo's first crude sketches of sunspots 4 centuries ago. But it does mean that anyone tempted to think of the sun as a fully solved problem, a simple, well-behaved fusion furnace whose behavior humanity has essentially figured out, should probably reconsider that assumption, at least until the next cycle has had its chance to reveal whatever it is still hiding, and quite possibly for a good while after that as well. If you found this exploration of our sun's unexpectedly turbulent cycle interesting, sharing it with someone who might enjoy learning about it, or leaving your own thoughts on which of these open questions you find most compelling, helps far more than you might expect in bringing this kind of careful, evidence-based science communication to a wider audience. And if you would like to keep following along as new data comes in from these ongoing missions, subscribing means you will not miss it when the next piece of this puzzle falls into place. Whether that turns out to be a fresh clue about the true depth of the solar dynamo, a revised forecast for cycle 26, or the next set of images from a spacecraft venturing somewhere no one has ever managed to look before.